In a small African village, a tired doctor from Médecins Sans Frontières reflects on another day of vaccinating children against rotavirus. She knows the vaccine's only about 60% effective, and that's okay for now. But she's been carrying around a burning question. Why is it that vaccines are not more effective? Tomorrow, this same doctor might assess women for cervical cancer. That's a disease that can be prevented with modern vaccines. She wonders how lives would be different if vaccines were cheaper. In California, a wealthy citizen takes in his distant view of Mexico. He's very concerned about news reports of a new influenza virus just across the border. He's had his annual flu shots, but everyone knows that they protect against what's happened, not what's coming. What to do? He wonders if the most powerful nation on earth can make a vaccine quickly enough to protect its citizens. These scenarios happen every day. The first two happen every day. The third one happens now and again. Some of you recognise that the California scenario is not fiction. It's the reality that was the 2009 swine flu pandemic. So why is it that our vaccine system has these three key weaknesses of effectiveness, speed, and cost in the 21st century? That's not an easy question to answer, or the very clever and good people of the world would have solved that problem already. And there's some great work going on with the Global Vaccine Alliance and the Gates Foundation. But one area that's not being adequately addressed is the engineering of new and better vaccines and the systems used to make them. In fact, most of our vaccine system relies on very historic approaches to design and make new vaccines. In terms of vaccine design, we rely on the breakthroughs of Jenner and Pasteur from the 19th century. Basically, we take something bad, we make lots of it or something like it, we make it safe, we mix it with something that activates the immune system, and we inject it. In terms of how we make vaccines, our engineers take what's handed to them and they apply the best available techniques to scale up that basic 19th century paradigm. That's why we still make influenza vaccines using eggs. We grow the viruses in eggs as a starting point. This basic technique was developed in 1931 in the United States by two scientists called Woodruff and Goodacre. It was then improved by the Nobel Prize-winning Australian scientist, Sir Frank Macfarlane Burnet, again in the 1930s. So these historic methods are actually underlying the current production system for many vaccines. Nowadays, we've replaced the people in that picture with robots. That's so that we can handle more eggs. If you look at a current vaccine manufacturing plant, it looks like advanced manufacture, but it's actually not. The paradigms of the last century are at the heart of our current vaccine process. So it's time to rethink the way we engineer vaccines. 20 years ago, I was very fortunate to be a Fulbright Fellow at Berkeley. I had more hair back then, which I actually discovered was a requirement of being at Berkeley. And I had time to actually step back and study how small proteins assemble themselves into ensembles, or structures that consist of more than a single protein. You actually get some very interesting effects that occur when proteins self-organise into structures, functions that the single proteins just don't have. I actually got quite interested in how viruses self-assemble themselves, and then how the structure from that self-assembly process interacts with and activates the immune system. In fact, I got very interested in how a virus shell self-assembles itself. It's a very interesting process. And it turns out a lot of people have been interested in that question for quite a while. And so quite a lot of remarkable insights have come from the scientists over a number of years. So the science is pretty well established. But the engineering was not. And that's actually where the opportunity sits for modern vaccines, is to put advanced engineering capability around modern life science. You see, if you can take an advanced manufacturing technique and you can make an empty virus shell efficiently, you can actually make a vaccine very quickly. And if you choose the right manufacturing system, you can actually make a lot of that virus shell very cheaply. Using modern molecular engineering tools, you can then redesign the surface of that virus shell to make the vaccine more effective. And in making it more effective, you can also direct it to address different strains of a given virus, or indeed an entirely different disease. So that opens up a whole range of new techniques for us. Let me give you a specific example. It's one I published a couple of years ago with colleagues, and some of the wonderful people I've worked with over the years are shown across the top of this slide. What we did was we took a part of rotavirus. With funding from the Gates Foundation, we actually combined that part of rotavirus with another protein that builds structure, a self-assembled structure. In doing that, we deployed supercomputers to optimize the molecular design, and we chose a system that makes a lot of the protein very efficiently. In other words, an advanced manufacturing technique. The tools at our disposal also allow us to alter the surface of that virus shell so that we can make the vaccine as an exact copy of the local viruses in a given village that might be affecting the children. The sort of structures we made are shown here on the bottom of that slide. Each of those is about 50 nanometers in size, or about 1,000 times smaller than the thickness of a human hair. Importantly, these structures self-assemble in an efficient way in our manufacturing system under our control. We're not sure if these are the right structures. The initial results we've got in the lab are very promising, but we still have quite a bit of work to do. We've also looked at some other diseases, including influenza, and in that case, the sets of tools we've deployed allow us to make an unprecedented speed of response to new viruses. Now, I'm not standing here to tell you that the specific approach or the specific structures we've created are the right ones, or indeed even that the specific path we've gone down is the best one. It's one of many paths that are available to us using these sort of new tools that we now have. What I have learned over the years, and I'm here to share, is the discovery that there are a range of new advanced technologies, surprisingly, that have come since the paradigms of the 19th century. In other words, since those breakthroughs of Jenner and Pasteur, we have new analytical techniques. We can see things much smaller than a human hair. We have the ability to sequence and manipulate DNA in a way that we've never been able to do before. And we can design proteins using supercomputers. Using modern nanotechnology and biotechnology, we can make almost any structure, and we can do that at a scale that has real positive impact in society. Since that collaborative work of the 1930s between the United States and Australia, the world has become even more connected. That connectivity helps viruses spread. It also helps our scientists and our engineers collaborate globally. And ultimately, that's where the future breakthroughs are going to come from, through the exchange of ideas of people, disciplines, and nations. In this connected world, my aspiration is to see technology unleashed to make vaccines faster, cheaper, and better.